Thank you for coming, everybody. And I'm very pleased to introduce Michael Douglas, who's at the CMSA at the moment, and also at Stony Brook. He's going to give us a talk on topics in computers and mathematics.
Thanks, Michael. Thanks, everyone, for the opportunity to speak about this recent, but I think very important topic. Let me, because the talk's going to cover so many things, I'm going to start with a sort of a narrative of, where are we going with all of this? So, okay, so if you think about, the mathematical sciences very broadly, there's many ways you could sort of classify or think about the progressions of what we're doing. One starts with exploratory work, and one makes it rigorous, eventually becomes mature. There's some arguments and problems are very simple, some are intricate. And then you see barriers in the progress in these various dimensions. And when one sees such general barriers, one wants to have general answers. And the answer of the moment, indeed, arguably the answer of the last decade, and this decade is coming from computer science and machine learning and AI. And the theme of this talk will be to describe several points of the many where computer science and AI interact with more perhaps traditional topics and mathematics, coming down to the most basic of how do we prove a theorem, and to argue that this is going to be a big deal. It's already a big deal, but it's going to be an even bigger deal. And in particular, I'll focus on this question of interactive theorem proving for the second part of my talk. And so here's the more specific outline of sections. But let me start with geometric PDE, and how more fitting could one be at the CMSA. And well, the original geometric PDE, of course, was Einstein's equations. And now we have many examples of this. And from a mathematical point of view, these are interesting equations for many reasons. And one is that solving them gives you canonical representatives of what some a priori more general structure. You could look at differentiable manifolds, and you could say, what's a special metric, so that if I want to classify manifolds, I can get the structure from the structure of those special metrics. And the Einstein metrics are clearly a natural category to look at. And they arise in many ways. One can define flow equations that lead to in principle, to Einstein manifolds, and is a great success in many directions, and most famously in the classification of three manifolds. So, well, that's a common theme in math and physics. And where does it come from? From both points of view, you'd like to get a flow from a action or an energy functional that you're doing a gradient descent. And well, the Einstein action, the thing that you might think would provide that, is actually false. It's a well-known problem that I'll get back to. And there are functionals that are obviously positive with critical points r, which equals 0, but they have many extra critical points. Okay, so again, one can go many directions, and the direction that I come from is supergravity and string theory. It adds a lot of ingredients to this type of problem. Okay, there's the idea of special holonomy, its relation to spinors. There's the interesting corrections that come from the extended nature of the string that define the deformed equations. Professor Yao has worked a great deal on these deformed equations in recent years. This last one is probably the least familiar, the dilaton work factor. What's that? So, again, without going into great detail, string theory, supergravity have many extra fields, and in particular scalar fields. And either a priori part of the theory, or, for example, the volume of the extra dimensions, or in the particular case here, what's called the warp factor, the idea that if you have some compact dimensions combined with observable space-time, the overall scale in our space can depend on where you are in the extra dimensions, this idea of warp factor. And it turns out to be a very central thing for many reasons. And an example of a flow equation. So I've listed two more, or three that in some sense come out of physics. Perelman's arguments were at least motivated by physics. And then the string compactification leads to various natural action functionals. And I've written the second equation here is an actional functional that I wrote and studied with Desconsi and Pigali some years ago that is bounded below. Okay, so this is an analog of the positive energy theorem of Shane and Yao and Witten and general relativity. And in fact, a very direct analog. There's this idea of the Hamiltonian constraint in general relativity, that imposing that constraint makes what a priori is not positive or negative, not manifestly bounded below. In this case, it's an analog that doesn't require to be, that requires space-time to be homogeneous space, de Sitter, anti-de Sitter, Minkowski, but in return, you don't have to know the lower bound. It just tells you that there is a lower bound. And this is just like the basic question of stability of a string, which again, not as a string theory as I would like and as I feel we need. We have these established questions that we've been working on for more than 20 years in fairly similar ways. And we're starting to run into problems, I think, is really the honest statement that in many fields in the history of mathematics, one had an exploratory phase and then one stepped back and realized, well, not everybody was convinced, not every result was convincing. We needed to deepen our foundations and come upon, both common ground that people could agree on, techniques that people could agree on, and again, make the subject mature. So I described this progression of the history of a mathematical idea, and I think we're clearly reaching that point in string compactification. Not in string theory as a whole, because there are many frontiers that we understand much less well than string compactification. But here we start to have this need for foundations. Okay, so this is partly where I come from, partly going to be motivation for topics later that I get to. And of course, it's not by no means unique to string theory. Okay, this is a little bit of a, I don't know, indulgent slide that, again, a purely stringy topic that would be hard to describe purely in terms of geometric PD is this famous topic of mirror symmetry that dates back to 1990, and the famous conjectures of Kontsevich and Strominger, Yao, Zaslow. Okay, so this is a very algebraic category theoretical description of mirror symmetry due to Kontsevich that surprisingly can make direct contact with string theory. This was work I did in the early 2000s on understanding the category of Dirichlet branes, and the physical Dirichlet branes turns out to be branes that you can define a stability condition, just as Mumford did for, say, moduli spaces of natural algebraic objects to make those problems well defined. It turns out that string theory is much more easy to find the stability condition than to actually write down or solve the equation. So this was made rigorous by Tom Bridgeland in a very again influential direction in mathematics. The geometric PDE analog, which we don't understand either fully, and this one equally important but hard to understand, is the SYZ fibration, that you have a picture where a 2 n-dimensional manifold is a fibration over some base by n-dimensional tori, and then you can directly act on the torus. We know how T duality in string theory acts on a torus, and then that's hard to study explicitly too. Here you need to really grapple with the geometric PD, and just Einstein, Kähler Einstein's just the starting point, and then the solutions. Even K3 is not very simple, and then even the simplest Fermat pointed hypersurface in P4 is an intricate solution with B3 equals 204. And how does one work with this? I've done explicit descriptions of that manifold due to my collaborators, Mark Gross, Bert Siebel here, but it's very intricate. And this is the point where the second dimension of simple to intricate starts to stand in our way. As a mathematician, you might say, well, I develop a general method. As a physicist, we tend to have to actually compute numbers, predictions that come out of our theory. And so, from both points of view, you would want, but especially I think from a physics point of view, you would want a explicit and general method, something that doesn't require a huge amount of new work for each example. And so that's the point where it's very tempting to go to a computational approach, a general computational approach. And of course, this type of question for curved space has been worked on for a long time. The famous idea of a Reggie calculus, updated by many authors, including McDonald, Miller, Alcindor, and work of almost 10 years ago, where they were able to formulate the Ritchie flow. And this is explicit simplicial complexes. Again, they're still complicated. There's comparable work, which I would say is in some ways conceptually simpler, that is much more used in practical applied math and numerical analysis. All with Winter, a number of other authors. You start by defining differential forms, and both of these, you require some sort of explicit simplicial decomposition. It's not really very easy at all. And there's this alternate strain of work throughout numerical PDE that says, let's not represent the space, let's represent the space of functions in some simple way. And in these problems in algebraic geometry, what that translates into is a method that starts with a canonical embedding, and in particular for a Kähler manifold, the projective manifold, you have a Kadara embedding. You choose some line bundle, you take a basis of sections, a positive line bundle, and then you take the family of Fubini-Studi metrics on that projective space that you embedded into and pull it back and get a family of trial metrics that you can then use as the basis for your numerical methods. Now you've got some finite dimensional approximation, but not based on explicitly discretizing or finding a simplicial complex for this space. It's a finite dimensional approximating space straight away of metrics. And this was taken up initially by Hedrick and Wiseman, and very, this is very much inspired by work of Simon Donaldson in 2005. Again, inspired by developing his own program of balanced metrics for constant scalar curvature and the like. And so this is, well, again, this broad family of computational tools for curved metrics, and I'm describing this one as a way into these problems that we would like to develop, and we have developed for string theory. Okay, so what's a very straightforward way to run with this idea? We've got the Kadara embedding, we've got the pullbacks of the Fubini-Studi metrics. They're parametrized by this explicit matrix H in the expression here. Well, the straightforward way, not always the best, but the straightforward way to solve a problem like this is to write a loss function or error function and minimize it. And of course, you could take Ritchie, but now in the particular case of Ritchie flat Calabi-Yau, there's a simplification you can make. So this is the case with a non-vanishing holomorphic three form in the case of interest in string theory, dim-C M form. And so the defining feature of such a manifold is that you have two volume forms. You have the standard Kähler volume form, and then you have this second fixed volume form, the holomorphic M form, with its complex conjugate. And you can show that the Ritchie flatness condition, SU3 holonomy, means that there can only be one volume form. There cannot be, of course, a ratio would define a scalar, which would have to be constant in this case, and would define another, U1 factor holonomy group that were not constant. And of course, in a compact manifold, couldn't be non-constant in any case. So that ratio with the property normalization equals 1 is a suitable loss function. Okay, so then finally, we've said we don't want the intricacy of explicitly describing the manifold by some simplicial or patch decomposition. To avoid that, we can just give a Monte Carlo estimator. We can say, let's sample points from the manifold, and let's take the average of a function over the points as the estimator of that integral. And then we're going to minimize that integral, okay? And why do we do all this? Okay, well, it will turn out, and I'm going to show you this momentarily, that when we phrase the problem this way, this is exactly a problem of machine learning, okay? And that we can just take standard machine learning software and you know, write 2 more pages of code and solve this, okay? Let me come back to that, okay? And say, you know, again, why do we want to do this? You know, what are the features, and you know, what made this problem difficult? Didn't I tell you we'd already worked on this in 2005 to 2010? You know, why is the problem not solved? And now we get into the very general obstacle that a great deal of numerical analysis, and in particular, you know, numerical PD has to deal with, which is the curse of dimensionality. Okay, so we, in the case at hand, have postulated some embedding of degree k. So sections could be degree k polynomials, and the number of coefficients of this matrix is going to grow with the degree k as k to the power real dimension of the manifold, and that's very rapidly growing. That's this curse of dimensionality that says that whenever we take any straightforward finite approximating space to functions in d dimensions, where straightforward can mean local products of systems, you know, basis functions in the individual dimensions, as in this sum I wrote there, you know, and you know, almost anything straightforward that you can think of, the number of coefficients in that expansion is going to grow as some degree to power the dimension. And you know, already for 3 dimensions, this is why one has supercomputers in the national labs to do you know, fluid dynamics simulations and you know, plasma simulations and so forth. And our problem with d equals 6, this is really the limiting factor. And then, of course, this is small peanuts compared to problems in you know, high, you know, say the many body physics, and in particular in machine learning. Okay, so now what's a canonical problem that was really the one that opened this machine learning revolution in 2012? It was the ImageNet challenge to take the series of images from a curated database. I put CFAR10, which was about the same time, but ImageNet was this, you know, big news item. So we were given 32 by 32 pixel color images. So each pixel is defined by 3 real numbers, red, green, blue, and we give it to the computer and we assign each one. The computer has to learn to assign each one to one of 10 classes in this data set, you know, cars, birds, cats, and ... And so what is it learning? Well, from a mathematical point of view, it's very simple. It's learning a function from r to the 30, you know, 1024 times 3 to R10, the probability, you know, sometimes the probability that the image lives in one of these 10 classes. Okay, well, again, easy to write, but curse of dimensionality to the extreme power. Okay, so what was the breakthrough? The many breakthroughs, obviously, that solved this. It was, the core of it was the use of feed-forward neural networks. Okay, so composition. Probably many of you have seen this, but I will very quickly review it. That's one has a family of functions defined by alternating linear maps, W. You can think of multiplication by explicit matrix with some sort of fixed nonlinear map. And I've written an example on the bottom line here, this so-called ReLU function. If x is positive, it's x. If x is negative, the function produces 0. And then we do that component-wise for one of these big vectors like R3072. And then because we have this series of linear transformations that we can choose, it depends on the basis who drops out, and we get this interesting, slightly random seeming, but certainly interesting family, parameterized family of maps. And an image recognition you might use to apply the translational symmetry of images, but the idea is still the same. And then we're going to solve, in this case, the supervised learning problem to say, how do we train it? We give it images with the correct class label, and from just that data it's supposed to learn. And what is it learning? Well, it's learning by minimizing, again, some sort of error or loss function, which in the simplest instance will just be take a list of these images, count the number of images for which it found the wrong class. Of course, we might use, it would be something more sophisticated in real life, but that's the idea. And gradient descent on that functional, believe it or not, converges to something reasonable, which classifies these images. Again, we're used to it now after 10 years, but it's just amazing. And this is, as you know, a very, very significant topic in computer science and applied math. What class of functions can these feed-forward networks approximate? How did it solve this cursive dimensionality? We don't have anywhere near a number of coefficients of some number to the 3072 power. How can we optimize this very horribly non-convex function with such simple methods as gradient descent? There's a much deeper question, which your colleague Buzz Barak and many others have worked on in great detail, that there's in practice, not only does one use networks like this, one uses networks with huge matrices, over-parameterized, many, many more parameters than data points. And then if you go to a statistician and tell him you're doing that, he'll say, that's ridiculous. That's a model that will overfit. You are wasting your time. That's one of the reasons that if you go to 20s, people did not think these neural networks were even worth studying. They just knew this argument, and they saw that well, either you can't optimize it or it's going to overfit, but it works. And it's still, to a large extent, an open question as to why this works, why this traditional dogma of statistics turns out to be kind of wrong in this case. Okay, so very interesting. How does it relate to what we were talking about before? And of course, many aspects that I touched on, such as the cursive dimensionality, relate in a clear way. And then an even more direct way is that the practical usefulness of this stuff is such that there is now extremely efficient and cheap computer hardware for evaluating these neural networks, these loss functions and the like, and you can buy a GPU, and instead of playing Minesweeper or whatever on your GPU, you can use it to solve a machine learning problem, and it's as fast as a supercomputer would have been 20 years ago. And so, of course, it's very tempting to apply this to many, many problems, and in particular numerical PDE. And you would like to formulate it in the same way that we just formulated supervised learning. We like to propose a loss function, such as how accurately do we solve our equation, and we would represent the unknown functions using feed-forward networks. And then again, this has been quite successful, but in a way that whose scope and limitations is really not it's just in its infancy, understanding it. So a few comments of recent work. So why in what cases do these feed-forward networks break this cursive dimensionality? Is it using the regularity of a solution of a PD? Is it because the solution might be smooth, as it was in the case of the Ritchie flat metric? Well, no. In fact, this has been studied in some detail, and there are fairly general assumptions. This does not. You still have the same cursive dimensionality if you have a CN for some fixed n. And people are starting to propose other senses of regularity. I find interesting work by Ian Wojtowicz in the past couple of years that argue that the core of what's going on with these neural networks is it's analogous to Monte Carlo integration. So it's just probably familiar. You sample, this is kind of clearest in statistics. You do the integral by sampling the way that we discussed earlier in the Calabi-Yau, and you get very general error bounds having to do with the variance, by definition of the integrand, but not depending directly on the dimension. And when you evaluate this combination of put the function through some linear transformation, get these many components and apply a nonlinear function, and then linear transformation. In some sense, you should think of the sum over these intermediate dimensions, the basis implicit in this dimension of theta, as something like an integral, which I've indicated by this integral dx in the notation here. And so by doing that integral, you're gaining the benefits of Monte Carlo. And then that type of approach predicts that even taking random features here will give you some of these benefits, which turns out to be true. Oh yeah. So to finish this story, which was kind of half of the talk, we implemented this. We need various K, although you can show that, again, the metric is smooth. This is a spectral method. So you expect exponentially good error, but nevertheless, you have to represent small features in the solution in general. Again, string theorists, algebraic geometers will know that you have singularities, and the simplest case of the hypersurface being an ordinary double point. In this case of a 3 complex dimensional manifold, you get a small real 3 cycle with a controllable size, and then the curvature grows, blows up into singular limit, but grows as the inverse size of the cycle to an appropriate power. And so if you're interested in limits with these small 3 cycles, which as a physicist you are, you need to be able to represent this, and you need to be able to at least talk about small scales and large degree embeddings for pieces of the manifold. So you might be tempted to go back to the simplest decomposition and then just decompose those pieces of the manifold in a more final way. But again, this is extremely intricate. And what you can instead try to do, and this is what I've done with my students, just take the neural network and adapt it to this type of problem. And the problem here being find a natural sub set of the holomorphic sections that we use for the embedding, or in fact, what works better, take a natural subspace of bihomogeneous functions, products of a holomorphic section times a complex conjugate, such that exactly the HSS bar that you were summing to get the general function that produces a Kähler potential. If you can produce a large enough subset of these things, you should be able to get the same numerical benefits that this neural network approximation gave for these other real PDE and machine learning problems. And this turns out to work. Again, I don't want to go into the details. I've spoken about this in other contexts, but this gets into an interesting theoretical question, which I've been trying to study mathematically, which is, what is it that, again, the same question that these others are asking, but in our context, what controls the accuracy of this approximation? Is it the depth? Is it the number of coefficients of this network, the dimensions of these intermediate spaces? Is it properties of the function that we're trying to approximate? And we get real information about this, which in this problem, which you can understand in great analytic depth, is again, I think a much more significant indicator of what's going on than most of the applied problems that you might try to study in this way. Not that they're not important, but this is a far more natural mathematical problem. And then this graph, again, I don't want to go into, this is error function of basically the smallest distance scale in the manifold. And this is giving evidence that indeed these many properties are important, and that there are cases where you do not really break the curse of dimensionality. There are functions where you need that large number of coefficients to approximate it. And again, data at this point, but data that will eventually lead to mathematics. Okay, so suppose we have that under control. Suppose we have a solution that as physicists we really care about. How do we prove that this corresponds to a solution? Well, there's the traditional arguments, the existing arguments, such as Yao and the many people that have worked on this based on a priori estimates. And there's theory that would allow us to take these numerical calculations and turn them into a priori estimates. And that is sort of the transition point to the second part of the talk, which is how can we turn such results, and how in general can we arrive at computational proofs in mathematics. And I'm just going to briefly review to kind of distinguish topics now that I was talking about numerical methods, topics that I will be getting into, topics that are very interesting, but I'm giving short shrift in this talk. Other language models I'll get, well, both of these I'll get into for our purposes. And there's a huge number of very interesting mathematical problems and applications that one can try to apply these models to, but let's focus on proof. So how would we make, what is computer-assisted proof, first of all? So computer-assisted proof is to say that we've carried out essential steps, and in particular, we've taken advantage of the computer to break the problem up into maybe 1 million little pieces that we can each understand, let's say by a linearized or by a tractable analysis. And then, of course, from a human point of view, that's useless. But from a computational point of view, that sounds very good. And then if you could rigorously verify the statement in one here that solving, proving the statement for each of these 1 million pieces proves the original statement, then you have computer verified proof. And I think the state of the art, and this is really a beautiful piece of work, is the solution of what Smale called his 14th problem, okay, but it was proposed before that, to prove that the Lorentz system is a strange attractor, okay, and the Lorentz system, a very simple 3-dimensional ODE, a dynamical system postulated, basically, empirically, is a little piece of a weather simulation by Lorentz back in the 60s. And it turns out to have this remarkable, but still relatively simple, dynamical behavior that on the one hand does converge to some much smaller space than the general space of initial conditions, but then within that space, small perturbations grow. And it's the sort of problem where, from some conceptual point of view, we feel we understand it, but the proof is intricate. It's very hard to capture the structure in some sort of general framework, but it's really not hard to capture the structure by cutting the dynamics of the space up into little pieces and checking it on each one. And then this was first done in the sense of computer verified proof by Warwick Tucker back in 2002, and very recently done by Fabian Imler, a postdoc now at CMU, in a theorem proving language, Isabel. So again, to show the scope, the kind of the range, but also what we can't do. It's an ODE, it's not a PD, but this is an example of what is doable with work now. So, interactive theorem proving, many of you will have seen something about it. There was a well-known 2008 notice of the AMS that laid out a lot of the basics. And formal proof goes back to, in some sense, Russell or Whitehead, but really Post and Gödel, to translate proof into a mechanical procedure, the answer to one of Hilbert's original questions that can be verified on a computer. So if you follow the right sequence of purely syntactic rewritings, it doesn't matter what these symbols mean, then you can argue that a given mathematical statement is proven from axioms. And then this is again, a fairly well-developed field in computer science, so much so that there are powerful systems that have been used to verify famous mathematical proofs, the four-color theorem, the famous work of Thomas Hales on his proof of the Kepler conjecture, the odd order Phi-Thompson theorem of group theory. There's a interesting developments in this, which that's where I'm headed. Again, I want to talk a little bit, perhaps not in the depth I wanted because of time, but enough to show you what this is, because again, it's a little fearsome at first, but then where is this going? Okay, so the systems that people use the most now are based on what's called a type theory, not set theory. So it's a more controlled framework. There's this idea of dependent type theory, which for present purposes, if you would like to make a definition that depends on a general vector space that doesn't require you to treat specially the dimension n as a number, but lets you say, I'm going to compose my definitions out of the base field and the dimension as an integer, and then have a type which depends on a type, such as the vector space depending on n. That theory has been very much developed and systematized. It has not answered all the questions. So the homotopy type theory, cubical type theory, try to do better in this, but this is more or less the state of the art in the existing theorem proving systems. And it has gotten to the point where mathematicians willing to put in the time find this worthwhile for their work. There's a list of fairly recent projects completed, the last one in progress. A very interesting work on Peter Schulze has a formalism that he calls a condensed mathematics, which I must admit I have not really understood myself yet. But if you look at his blog, you will find that a important proof in his work that he was worried about has been completed actually on May 28th by the community of mathematicians using this theorem prover lean. The independence of the continuum hypothesis is an interesting recent milestone that shows the breadth of these things. Not so much in ODE, PD, despite the beginnings of my talk. Here's at least a differential topology, the H principle. So the sphere aversion problem, there's a project going on to formulate and rigorously verify proof of that. Okay, so here is a few examples. And again, I want to stress that this is a work in progress. And I think the interesting opportunity here is that it's now something you can use with a fair amount of practice, a year of practice, or 2 years of practice. And by reading these examples of proof, so the middle block here is basically the statement that within a monoid, so we haven't assumed that there are inverses, but let's postulate that there's an inverse, the inverse is unique. And so the statement here is the top line of that middle block. It's pretty clear. That's what it says. Okay, then is inverse implies y equals y prime. So the third line there is the statement we're trying to prove. The fifth and sixth lines are instructions to the computer called tactics. And the key instruction is this one in the shorter version of this proof in the bottom line. So the same proof can be realized in this lean theorem prover in the bottom box. It's this Bolesock y prime xy. If you read that, that's basically saying that if you substitute in, you want to show x, you basically want to look at the product of y, x, y prime, and then use associativity. And then that will, simple algebraic manipulations will lead you to the proof. And so, the status of the system some years ago was that you had to give this middle block. You had to give a series of instructions to take various hypotheses, put them into the goal, rewrite, and so forth. And now the status is what it is on the bottom line, that you just give it that one hint, use associativity, and that particular series of products, and it will do the rest. Okay, so this is just to illustrate the sequence of steps. I'm not going to go through this in detail, but the sequence of steps that the computer has automated by that last line there. And so this is an active area with a number, many approaches trying to make these interactive theorem provers more intuitive, more organized, easier to use. And the particularly interesting that I get to at the end, this last one, really applying technologies of AI to theorem proving. Okay, this is a work that I did with Floris van Doorn, a tutor, as I said, the implementer of this proof of the continuum hypothesis, a very talented mathematician in his own right, but also tutored many of us at CMSA on a proof of a Maschke's theorem from a group representation theory that you can basically decompose into a direct sum of irreducibles. And if you can average over the group, it's not a hard proof. And again, for even a student, this is not a hard thing to understand. And then this is what you have to in the end tell the computer. So there are various definitions. There's this last block here, theorem Maschke, and again, it's something that if I had another half hour, we could work through. It's definitely understandable. It is more complicated. It forces you to work on a level of detail that spelling out many facts that would be obvious to us. Okay, this is actually proving that you can use the sum over the group to make a equivariant map, and this is the core of the proof. So what for a human would be relabel the variable of summation requires a certain amount more of spelling out for the computer. Okay, so one of the main lines of work, besides making these theorem provers smarter, more able to see what's obvious, is defining these library concepts. And this lean theorem prover has what was right now by far the fastest growing library, with about 100 contributors of various levels of activity, producing about 200,000 lines of this stuff per year. And it's really realized some sizable fraction of the writer, the French undergraduate mathematics curriculum as proven, verified proofs in this lean math lib. Okay, this is an example of the kind of structure that the computer has learned. And this is basically the hierarchical structure that if you ask what aspects does a norm field, the definition at the top? Well, it's a normed ring, it's a norm group. It has many, many levels of hierarchical structure. And then, of course, if we looked at the actual proofs, we would get many more levels of structure. And so I'll come back to this question. Does this tell us something about the actual structure of mathematics? Okay, well, I mean, it really must, And the question that I would like to pose, which I'd like to hear to what extent this has been posed in previous work. We're very now, of course, the central idea of mathematical logic is that mathematics can be reduced to logical statements proven from axioms. But of course, there's an infinite number of these statements. There's an infinite number of not just tautologies, but totally trivial tautologies. Given A, we know A or B for any B. Those are not interesting tautologies. Some of them are interesting. And what is it that determines the interesting ones? Well, for some, you could say, well, I had to prove X. This was a statement along the way to proving X. But why did I prove X? Some statements are so interesting that we feel it's valuable to teach them to people. It's valuable to teach them to the computer, it's valuable to teach them to people. There really should be some way of saying that precisely enough to put it on a computer. So how do you say that? Well, I'll come back a bit to later. Okay, so before I come to that, I'll ask some less philosophical questions. Well, how can this help us in our jobs? Well, we don't just do research, we teach, and there are many computational textbooks, and really the interesting acid test of any of this is to teach an integrated course where you don't assume that the students already know group theory or PDE or whatever it is very well. They are learning the tool to help them learn group theory or PDE. And this is, if you've ever tried to do it, it's very hard because these computational tools all require a great amount of detail. And as you saw in the case really don't contribute to understand mathematics. So what do we do about that? And here's a prototype I like to give. This is about 20 years old. Sussman and Wisdom, Structure, Interpretation, and Classical Mechanics. And this is not about proof. This is really about astrophysics and computational methods. So they are describing up to chaos theory for physicists, and they show you how you can both give the concepts and give the numerical and the computational methods at the same time. So it's a very inspiring group. It's been a popular course at MIT for about 20 years. I think this is an important near-term goal for this field of computer math, interactive theorem proving. If you can't combine it with a textbook and teach it to students in the same way that you teach the rest of the material, it's too complicated. It will never really have the life that it should. And I think this is something I've thought about. I've made baby steps. I think this is an underappreciated problem, which I would like to convince more people. Okay, so this is an example of the sort of thing that you would have to add to Lean, where Lean is very weak on giving explicit examples. Okay, and this is kind of what you would have to do in Lean as it stands to give one of the basic examples in the second chapter of Jacobson of a transformation group. And well, it's not terrible, but this is the sort of thing that students need. The computer perhaps needs to. How do you express it well? Okay, another very interesting frontier is what's Tom Hales has been working on for some years, what he calls the Formal Abstracts Project. And so this is to create an online repository of statements of results of mathematical papers without the proofs. Okay, so what you might say, well, what's the point? There's no proof, but the point would be to record, to be able to search, to have something like the mathematical reviews, but again, in the way that the computer can not just read, but understand deeply, because the statements of the theorems will be formalized precisely. And he's developed this quite a bit, so it's easier than this problem of verifying all of mathematics, but still very non-trivial. I had many discussions with him a couple of years ago, and it's something which I'm convinced a focused effort could do in 5 years. And again, we'll see. What he's been working on most recently is what he calls a collada, which is a controlled natural language. And so this looks like ordinary mathematical text, Silas theorems, but this is actually something the computer can also read. This can be directly translated into the ITP languages that I described before. So it's a challenge to make a grammar that people can both write and that the computer can understand, that he and a number of groups are taking up. Okay, so well, I mean that's I think a short but hopefully interesting summary of the status of interactive theorem proving. It's not at the point where I could use it to prove my string theory problems, but it's making rapid progress. And you know, where is it going? Well, clearly the key problem is, you know, that we have to give too much detail. What is extremely obvious for us should at least be kind of obvious for the computer. You know, if you can't do that, then it's maybe not ready yet. And many computer scientists are working. In fact, some of the leaders in artificial intelligence, Ilya Sutskever, who's the head of research at OpenAI, Christian Szegedy at Google, who invented many of the basic technologies, think that this is the key problem for the near term in AI. And they have very active research groups at their respective companies trying to do this. And well, what's involved? Well, you know, again, the basic analogy that you could try to make is that when you develop one of these proofs, so you start with a statement, you have a goal, you have to now either, you know, call in premises, you know, previously proved results which are relevant for the next deduction, or you have to make some sort of explicit deduction. And in these systems, you often choose a tactic. And these are like moves in a game, okay? And so how could you, you know, use that analogy? Well, in other versions of this talk, I put up a slide about AlphaGo. You know, what was the most famous AI result of perhaps all time at this point? You know, it is AlphaGo, which was solving this two-player game of Go at a superhuman level using reinforcement learning. So it's definitely, it's hard to argue with people that say that, you know, the potential of this technology has not yet been, you know, explored, or we don't know its limits. So it's certainly a very well-motivated approach to try. Another approach, which is they're doing at OpenAI, is to use the language model. So if you had, for example, GPT, recall these stories about the program that reads text and produces fake newspaper stories. The most famous one was GPT-2 from OpenAI. They're up to GPT-3, and there's GPT-F, which works with normal mathematics. And there's a group using that to produce subsequent steps of proofs. And then there's a sort of a symbolic, old-fashioned AI approach called the sledgehammer. That is, you take the step of the current proof, which is, you know, again, not easy, you know, impossible to automate in higher order logic, but you extract out a problem in first order logic, which is a much more algorithmic subject, and then you try to solve that. And so again, you know, they're making progress. They can prove up to 70% of the short lemmas. There is a, you know, you can download these tactics and substitute some reasonable fraction of this hard to read tactical text of the proofs with by sledgehammer or by GPT-F. Okay, I'll talk a little bit about some work in progress, and then I'll finish, coming back to this question of how do you define interestingness in mathematics. And I've given another motivation. I skipped this a bit, which is that, of course, one of the key elements of the success of AlphaGo and AlphaZero is this ability to do self-play. The machine can play itself and go. So what does self-play mean for a mathematician? Well, we do it. We do it all the time. But what we do is we mull over, we look for interesting stuff, right? You know, so obviously the computer has to have some ability to do that. So what does it actually mean? And so a reasonable starting point would be to follow the idea of Kolmogorov complexity and say that, well, it's hard to know how interesting something is, but we can define how useful a statement is by asking how much does it shorten the proofs of all of the other statements. If it shortens lots of other proofs and it's not that long itself, then from some point of view, it's useful. That seems like a clear definition. So could that be interestingness? Well, probably not, because you can look at a statement and say, that's boring, that's interesting. And this criterion that I just gave is actually quite hard to compute. You have to sample at least a huge set of proofs, so it helps you to prove them. But rather, what interestingness is this concept of reinforcement learning, that the system has to not just play through games in the case of Go to decide whether it's going to win or lose them. It has to develop this function that decides, you know, what's the score of the position, you know, how likely is it that this position, that the move I'm about to make increases the chances that I will win. And the theory of reinforcement learning in large part is the theory of learning such functions. And this function is what we would advocate is the underlying formal representation of interestingness in mathematics, and perhaps based on utility, although one can make other identifications besides utility. So there's a project of cryptomorphism, which again goes back to Harvard, the idea that one should be able to, one knows that one can represent the same mathematical structure using many signature axiom systems, which are not obviously identical, but they are cryptomorphic. So can the computer recognize that? That is an intimately linked problem, that turns out. Okay, so that's my overview, and let me just close with a few reflections. That this is is this mathematics? Well, I mean, it sort of is, and it sort of isn't. There is this very motivated group of younger mathematicians who are attracted by Lean and the other theorem provers, are really pouring their hearts into it. There clearly is something there. Clearly the work proceeds in a different way than it does with the traditional mathematics. It's less by, people do publish papers, but equally people do this kind of build up the library, edit this, improve that, and the way Wikipedia works. And so it's not the same thing, but I would argue it's mathematics, and that's going to have an increasing, and I believe before we know it, a large impact on the way we do mathematics and mathematical physics. Let me just close with a reminiscence. I was motivated, one of my many motivations for getting into this was friendship with Vladimir Voivodsky, like Voivodsky. And so he would tell me about these things from time to time. And of course, it wasn't what I worked on at all. So the discussion was very qualitative. And we developed this analogy with the role of technology in music, okay? And so clearly people started off by singing, in the human voice, and wind instruments. And then you look at this explosion of creativity from a Western perspective with Bach and Mozart, and Beethoven and like, and obviously there's an explosion of human creativity, but you certainly could point at the development of keyboard instruments as a important enabler of that progress that allowed a single composer to play with and experiment and develop harmonies. And that level of ease is what Voivodsky and what we should be seeking for the ability to work with proofs, and I believe that is coming. Again, in the beginning in this decade, and in not such a long time. So I'll stop there, and thanks for your attention, and ask the questions.
Thank you, Michael. We can all show our appreciation. I'm sure there's lots of questions. There was one already in the chat, which I'll just read out loud, and some hands are up. But so, oh, Giannis, you have your hand up. So maybe you just want to read your own question.
Yeah, thank you, Michael. I was wondering, what do you think about a quantum computing setting? Would this framework work there?
Well, that's an interesting question. I mean, the general belief, of course, is that quantum computing is not fundamentally so much more powerful than classical computing, and in particular that an NP, a hard problem, still is fundamentally harder and typically would take exponential time. And so for the problems that I'm talking about, I think that's the measure. If you tried to generate proofs by simple enumeration of possible proofs, that's like at least double exponential, and the quantum computer could not solve the problem that way. I mean, of course, it's one can try to formalize, and I think a very interesting question is, can a formal point of view shed a different light on quantum mechanics? People have worked quite a bit through the years of deriving the quantum mechanics from some sort of more conceptual set of axioms, such as Diach and many others did this. And I think a problem that I have tried to think about is to what extent could you motivate or define quantum mechanics without ever talking about complex and real numbers? I mean, are those really fundamental, or is there some way of defining the theory that still has the amplitude and the standard interpretation without putting in those numbers at such a low level?
Thank you.
Sherar, I'm sorry, I don't know how to pronounce your name.
Thank you. Shariar in the
Oh,
case.
sorry. Yeah.
That's all right. Thank you though. So I was just trying to compute actually. Yeah, this is the slide. I was trying to maybe the one. Yeah, I was trying to compute the interestingness of Deligne's proof of Ramanujan's conjecture that tau p is less than p to the 11 by 11 over 2, just because it's the simplest statement. And I cannot understand the proof of it, and because it requires so much, so I would like to understand what the interestingness of that is, or in general, what this
Okay.
measure.
You're saying if you're trying to prove a given, then even if the proof is very complicated and requires hard to understand intermediate steps, it's still interesting. Is that your point? And so how can this be the right definition?
Right.
Okay, a well taken point. I definitely agree with that. The whole story is much longer than this, and does require, at least a version of it that I have been advocating, coming in with other sources of problems. It's not the only source of interestingness.
I see.
Yeah.
I don't see other hands up, but so I have a question, Mike, and I think I've asked this to you before, but one of the places in pure math where I think computer-aided investigation would be really helpful is in the techniques that use higher categories.
Right.
Just the axiom system and the number of pieces of information you actually have to specify to describe anything.
Yeah.
It's very systematic, but it's very complicated, and everybody.
That's right. And there was some success with homotopy type theory and cubical theory.
Right. So there's So the communities are kind of merging, but I think that cries out for a different kind of tool. That's a tool that would, I mean, I would love to have a tool that, when I need to specify something in higher category, it just interviewed me for the structure and I just told it what it was and it checked that it satisfied the axioms, and then I could go on. I still want to make up my own proofs, but I want to use a complex axiom system that I want the computer to know the rules for me.
Yeah, well, it would be worth talking about. Again, I mean, I think the basics, you kind of have to work, give the computer some basic idea on the level I discussed, and then many things. The type of research I was talking about, what it tends to be is that these systems got to the point where you can give non-trivial searches and tactics, ways of looking for axioms, like this cryptomorphism problem I mentioned. And so once you've got the basic definitions, there definitely is scope for the computer to help at this somewhat higher level. And so it would be worth talking about, is anybody working on the basic definitions of what we talk about? Perhaps people could be interested in that, yes.
Yeah, thanks.
Sure.
So are there any other questions? I don't see any further hands up.
I can ask one.
Oh, yeah.
Okay. It's a fantastic talk, I thought, and a really great subject. You used the word interesting,
right.
And I wonder whether you could throw in surprising as well. Is there a milestone where something is not only interesting but surprising that came up in some example, and then we could study it?
Okay, so actual definite examples from either computer work considered broadly or through improving of something surprising. I mean,
say it again.
So as opposed to the sort of meta discussion I'm having, you might ask, how could you define surprising? Or you might ask, well, what in the work along these lines, what surprising things came out? I took your question as the second. Was that? I think in my experience of doing this, it's a constant series of little surprises. I don't think I've done it enough to encounter a big surprise, but what a very common thing that the experts in this will say, and in particular, one of the criticisms that's labeled of Tom Hale's project is that you make these definitions and you say, I'm going to make a precise definition without necessarily giving the proofs. It'll be much easier. And then people do that, and then they come back and try to make the proofs, and they realize that there's some major gap in their definition that really either makes it impossible or incredibly difficult to make the proof. And then they seem to learn something by doing that. And there are some excellent talks by Kevin Buzzard on this general topic. So one category of this sort of thing is what he calls the mathematician superpower of recognizing equivalences. That we make definition A, we make definition B, which looks kind of different, but we just immediately see, yeah, that's the same thing. And then that can sometimes be such a gap that the compute, just bridging it for the computer is just very, very difficult. So that's one type of surprise. And again, I'm not sure how interesting that surprise is, but it's definitely a surprise that seems to come out frequently from those.
Great, thanks.
Okay, well, if there's no further questions or comments, let's thank Michael again for a really broad and interesting talk. And I know some of us have meetings with him later this week. So thank you, Michael. And thanks everyone for coming.